In this video, we talk about techniques for evaluating limits at infinity when direct substitution doesn't give us quite enough information. And this is going to apply particularly to polynomial functions and rational functions. Let's start off with talking about polynomials. To evaluate limits at infinity of polynomial functions, analyze the dominant term of the function. Dominant term refers to the term containing the highest power of x, or the term that grows most quickly in the function. For example, evaluate the following limits. We have the limit as x approaches negative infinity of the polynomial 3x to the fourth minus 6x cubed minus x squared minus 10. Here we are evaluating the limit at negative infinity of a quartic, a fourth degree polynomial. Well, notice if we were to try our direct substitution, plugging in negative infinity here while raising it to an even exponent would give us a positive infinity. We would then raise a negative infinity to an odd exponent. That would be a negative infinity. Minus a negative infinity would be plus infinity again. Here, negative infinity squared would be positive infinity. So I would then subtract infinity, and then I would subtract 10. And so notice this combination of adding infinitely large numbers and then subtracting infinitely large numbers and subtracting 10. Well, this doesn't quite give us enough information as to what our answer is going to be. So instead, we can analyze the dominant term of the polynomial only. We evaluate the limit as x approaches negative infinity of 3x to the fourth power. 3x to the fourth power is the term with the highest power of x. That is our dominant term. And now we can try our direct substitution. This gives us 3 times negative infinity raised to the fourth. Negative infinity raised to the fourth, well, that's going to give us an infinitely large positive number. And 3 times an infinitely large number, well, that gives us a positive infinity. And because positive infinity is not a real number, we also write dne. We can do the exact same thing, evaluating the limit as x approaches positive infinity of this polynomial. Anytime you are dealing with polynomial functions, right, all you have to look at is the dominant term. We can forget about the rest of these terms. Analyze it as the limit as x approaches infinity of 3x to the fourth. Plugging in infinity for x, infinity raised to the fourth power, well, infinity times infinity times infinity times infinity, that gives me an infinitely large number. 3 times infinity gives me a positive infinity, dne for my answer. And we could verify this graphically. Remember that limits at infinity tell us about the end behavior. This is saying as the x values go to the left, the y values go up. The function rises to the left. As the x values go to the right, the y values go up. The function rises to the right. Let's look at another polynomial. To determine the end behavior of the following function, we have f of x is equal to 10 minus x plus 3x squared minus 2x to the fifth power. So when you read the words determine the end behavior, this is implying that you must evaluate the limits at negative infinity, the limit as x approaches negative infinity of the function f of x, and the limit as x approaches positive infinity of the function f of x. All right, determining end behavior implies that you have to evaluate these two limits. So let's start off with the limit as x approaches negative infinity. Well, we're evaluating a limit at infinity of a polynomial function. So what do we have to do? Limits at infinity of polynomials. We can simply analyze the dominant term. That is the term with the highest power of x, which is negative 2x to the fifth in this case. All right, the limit as x approaches negative infinity of negative 2x to the fifth power. We plug in a negative infinity. Well, negative infinity, if I take a negative and raise it to an odd exponent that stays negative, this is negative infinity. Negative 2 times negative infinity, a negative times a negative gives us a positive infinity, comma, dne for our answer. We can do the same thing when we evaluate the limit as x approaches positive infinity. We look at the dominant terms. Again, the rest of these terms don't matter when we're talking about really large values of x. the dominant term is going to control the function. So we have the limit as x approaches infinity of negative 2 times x to the fifth. We plug in infinity. Well, if I raise infinity to the fifth power, that still gives me an infinitely large positive number. An infinitely large positive number times a negative 2 gives me a negative infinity dne. So again, limits at infinity tell us about n behavior. This function, as it goes to the left, goes up, and as it goes to the right, it goes down. Let's now talk about limits at infinity for rational functions. To evaluate limits at infinity of rational functions, that's a polynomial divided by another polynomial, we analyze the dominant terms of the numerator and the denominator. Note that direct substitution yields the indeterminate quotient infinity over infinity. So again, direct substitution is not going to give us enough information, and we actually end up with some combination of positive or negative infinity divided by positive or negative infinity. And that is another indeterminate quotient. We've already talked about the indeterminate quotient 0 over 0, okay? The indeterminate quotient positive or negative infinity divided by positive or negative infinity. All right, we must also do another technique. So evaluate the following limits. Here we have the limit as x approaches negative infinity of 3x plus 2 divided by x squared minus 1. Notice if we try our direct substitution, in the numerator we would get negative infinity, and in the denominator we would get positive infinity. Right? And again, any combination of positive or negative infinity divided by positive or negative infinity is indeterminate. That means we need to try something else. So what do we have to do? Analyze the dominant terms. I can rewrite this as the limit as x approaches negative infinity of 3x divided by x squared. 3x is the dominant term of the numerator. X squared is the dominant term of the denominator. Notice this still gives me negative infinity divided by positive infinity with my direct substitution. But we can do algebra. There is a common factor of x between the numerator and the denominator, which we can divide out, leaving us with the limit as x approaches negative infinity of 3 divided by x. We can now complete our direct substitution. If I have 3 and I divide by an infinitely large negative value divided by negative infinity, remember, any real number divided by positive or negative infinity is going to equal 0. We can do the same thing for the limit as x approaches positive infinity. Again, direct substitution gives us an indeterminate form. We would end up with infinity divided by infinity. Indeterminate means we need to do something else. Because we are dealing with a rational function, a polynomial divided by a polynomial, all we have to do is analyze the dominant terms. Again, we still have infinity over infinity, but if we do algebra and divide out our common factor of x, we have the limit as x approaches infinity of 3 divided by x. 3 divided by infinity, well, that is equal to 0. So what is the end behavior of this rational function? Well, as the graph goes to the left, the y values are going to approach 0. As the graph goes to the right, the y values are also going to approach 0. And we can verify that with a graph of our function. And also make note, we have a horizontal asymptote here at y equals 0. Yes, remember that if you evaluate a limit at positive or negative infinity and the limit exists, you have a horizontal asymptote at y equals that value. In this case, y equals 0. Let's try another one. Determine the end behavior of the following function. Again, this means evaluate the limit as x approaches negative infinity and the limit as x approaches positive infinity. Identify any horizontal asymptotes if they exist. So we are evaluating the limit of a rational function. Again, if we just tried our direct substitution, notice we would get some infinitely large number in the numerator divided by some infinitely large number in the denominator. Infinity over infinity. That is indeterminate. But we can simplify this by looking at the dominant terms. The dominant term of the numerator is 40x to the fourth. That's the highest power of x. 10x to the fourth is the dominant term of the denominator. Well, With our direct sub now, we still end up with infinity over infinity, but there is algebra that we can do to simplify the expression. 40x to the fourth divided by 10x to the fourth. Well, x to the fourth over x to the fourth, those are going to divide out. And 40 divided by 10, well, that just leaves me with 4. This is the limit as x approaches negative infinity of 4. And the limit of any constant is equal to that constant. We can do the same process in evaluating the limit as x approaches infinity, positive infinity in this case. Again, it's a rational function. Limits at infinity for rational functions, we look at the dominant term of the numerator and the denominator. We get infinity over infinity, the indeterminate form. We can still do algebra to simplify. This becomes the limit as x approaches infinity of 4, and the limit of a constant equals that constant. So, what about our horizontal asymptotes? Well, again, if you evaluate the limit at positive or negative infinity and you get a real answer out, you have a horizontal asymptote at y equals that value. So in this case, we have a horizontal asymptote, y equals 0. Again, we could verify this answer with a graph. Here we have the graph of the rational function f of x. As the function goes to the left, the y values get closer and closer to 4. As the function goes to the right, the y values also get closer and closer to 4. Let's look at one more example here. There's our horizontal asymptote, y equals 4. All right, determine the end behavior. Again, this means find the limit as x approaches negative infinity and as x approaches positive infinity. Identify any horizontal asymptotes if they exist. So we evaluate the limit as x approaches negative infinity of 1 minus 2x plus x cubed over 4 minus 2x. Again, we are dealing with a rational function, a polynomial divided by another polynomial. So to evaluate this limit at infinity, we are going to look at the dominant terms. Dominant term of the numerator is x cubed. Dominant term of the denominator is negative 2x. Make sure you include the sign that comes in front of the term. Well, if we try our direct substitution, we get negative infinity divided by infinity. However, we have a common factor of x that we can divide out. So do your algebra first. If we divide out an x from the numerator and denominator, we now have the limit as x approaches negative infinity of x squared divided by negative 2. If we plug in negative infinity now, we get negative infinity squared. Negative infinity squared, well, that's going to give me a positive infinity. Positive infinity divided by negative 2. A positive divided by a negative gives us a negative. Negative infinity, comma, d and e is our answer. Now, evaluate the limit as x approaches positive infinity, right? This is what does our graph do as it goes to the right? Again, limits at infinity for rational functions. Look at the dominant terms. The limit as x approaches infinity of x cubed divided by negative 2x. This gives us infinity divided by negative infinity, which is indeterminate. However, we can do some algebra to simplify the expression. The limit as x approaches infinity of x squared divided by negative 2. We do our direct substitution. Infinity squared, well, that just gives us positive infinity. Positive infinity divided by a negative 2, that's going to give us a negative infinity, d and e for our solution. So in this case, do we have any horizontal asymptotes? No, the limits as x approach positive and negative infinity did not exist. We did not approach a unique number L. Therefore, we have no horizontal asymptote. And we can verify this with the graph. Notice as the graph goes to the left, the y values go down to negative infinity. And as the graph goes to the right, the y values go down to negative infinity as well. All right, so there you have evaluating limits at infinity for polynomial functions and rational functions. If you are evaluating a limit at positive or negative infinity for a polynomial or a rational function, all you have to do is analyze the dominant terms.